All right, so really the guidelines are this four-step process, which to me, I always laugh when I put this slide up because I read it and it almost reads as like condescending. Like, okay, here's how you solve a problem. Understand the problem, figure out how to solve the problem, and then solve the problem. But it really is just supposed to organize your thinking. So understand is like, okay, slow down and make sure you understand the problem and what you're looking for. So you guys were doing that, and you did a good job of it when we were doing the labyrinth problem. You were asking questions that helped clarify kind of what our end goal was, right? Things like, can we just ask one of them what's the correct door, and then okay, so why doesn't that work? That helps clarify your thinking on what the parameters are and what your solution type of solution you're looking for. So then devise a strategy for solving the problem. Step 3, carry out your strategy and revise if necessary. And then step 4, look back at your result, interpret, and explain. So I like to think of this as check for sanity. Make sure your results are sane, that they make sense. All right. Go ahead and give me a green. All right, so when I say understand the problem, and you don't need to write all these down, again, these slides are available as a PDF under this week's module. That can mean a couple things. So think about the context of the problem to gain insight, make a list or table of specific information, draw a picture or diagram to help make sense of the problem. That's what I did for the Die Hard 4 gallons in the 5-gallon bucket problem. Restate the problem in a different way to clarify the question. Make a mental or written model of the solution. All right, some additional kind of corollaries for step 2, which is devise a strategy for solving the problem. You want to obtain any needed information that's not provided in the problem statement. Make a list of possible strategies and hints that will help select your overall strategy or map out your strategy with a flowchart or diagram. Carry out your strategy and revise it if necessary. This is one of my pet peeves with students and math. A lot of math teachers don't like their students to use pen. They want them to use pencil so they can erase. You shouldn't be erasing in math. You need to be able to see those steps, that when you make a mistake, you should just strike it one line so you can still read it, move down to the next line. So I often encourage just using like a blue or black pen. I think whiteboards are probably the best to do math on for that reason, though. But as I was trying to explain earlier, the only way to get to the right answers is through a series of wrong answers. So every time you screw something up, that's one step closer to figuring out the correct answer. And then check for sanity. So look back, interpret your result, explain it, and make sure the calculations make sense, okay? All right. Couple hints. Again, you don't need to memorize these, and this slide is available to you, so don't feel like you have to verbatim copy it down. There may be more than one answer. There may be more than one strategy. Use appropriate tools. So don't use hand computations if you're working with messy decimal numbers. Use a calculator. Hint number 4 is huge. Consider simpler, similar problems. That's often extremely helpful. 5 is kind of similar. Consider equivalent problems with simpler solutions. 6, approximations can be useful. 7, alternative patterns of thought. And then 8, don't spin your wheels. Sometimes it just takes, go take a walk, get your mind off it, then come back to it. All right, so this one's a pretty straightforward. This one's not super riddle-like. Pretty straightforward, but maybe not typically easy word problem. So I have tickets for a fundraising event that are priced at $10 for children, $20 for adults. Shauna worked at the first shift at a box office, selling a total of $130 worth of tickets. However, she did not keep a careful count of how many tickets she sold for children and adults. How many tickets of each type did she sell? So here I might write down relevant information. I'm going to go C represents a child's ticket. And we'll select A represents adult's ticket. And so I think the easiest way to figure this out is come up with an equation to figure out how we get total cost at the door, right? So I know that child's tickets were $10. So if I do $10 times the number of child's tickets plus $20 times the number of adults tickets, that should get us our total door profits, right? Well, our total door profits were $130, right? And so all we need are values for number of child's tickets, plug in for C, and values for number of adults tickets that would satisfy this equation. But what we have here is two unknowns in one equation, which means that there could be more than one solution. Can anybody give me a valid answer, a value for C and a value for A that would satisfy this equation? C equals 1, A equals 6. Well, that would give me $10 plus $120, right? Because 6 times 20 is 120. It's 130. So I agree. Could be one child, 6 adults. What else? Three children, 5 adults. So that would be $30 plus $100. Yep, that works. One adult, 11 children. What about 13 children, 0 adults? There's more than one correct answer in this case. All right, let's do another one. All right, in this one, two cars are 120 miles apart being driven toward each other on a long straight highway. One car is going 20 miles per hour, the other is going 40 miles per hour. At the same time, a canary starting on one car flies back and forth between the two cars until they meet. Okay? The canary always flies 150 miles per hour and turns around instantly each time it reaches a car. So it's just oscillating back and forth between the cars as they approach each other. It's also a very fast canary, 150 mile per hour. How far has the canary flown when the two cars crash into each other? So this is one where you can kind of approach it from a different strategy. A lot of times what you want to do is just immediately think about the canary and go, okay, well, I need to know how many times it goes back and forth. And in this case, no, you don't. What you do need is a basic physics equation that I'll give you, which is distance equals rate times time. Hopefully you're familiar with that. Yeah. All right. So since the cars are driving directly at each other, we can figure out how long it would take them to meet, right? So since one's going 40 miles per hour and one's going 20 miles per hour, they're actually approaching each other at 60 miles per hour. Does that make sense? The other thing we know is that the distance they start apart is 120 miles, right? So times time. So I can divide by the 60, and that should allow me to solve for the time, right? I'm going to divide by 60 miles per hour. Divide by 60 miles per hour. And that's going to leave me with the time they'll take to reach each other is 2 hours. Okay. All right, so then for the canary, since the canary is going back and forth and it's turning around instantaneously, and I know how fast the canary is flying, right? The canary flies at a rate of 150 miles per hour, but it's going to take two hours for the cars to meet each other, meaning the canary is going to be going back and forth for 2 hours total. So I'll just multiply this by times 2 hours, right? Notice still using my unit analysis. So this is going to leave me in units of miles, which is what I want. 150 miles times 2 is 300 miles for the canary. Yep. Any questions on that? Give me a green check when you're good with that slide. All right, here's another one. So Juan is decorating for a party in a room that has 10 large cylindrical posts. The posts are 8 feet high and have a circumference of 6 feet. His plan is to wrap 8 turns of ribbon around each post, and we're trying to figure out how much total ribbon will Juan need. So the way we can kind of do this one, you see the way that the ribbon is wrapped around the post so that it's parallel to itself. We want 8 total turns. So if you think about cutting vertically straight down the post lengthwise and then laying it flat, the scenario we would have is this, right? Because this piece of ribbon would connect the other on the other side when we rolled it up. And so essentially the way we can think about this is that what we actually have, since we want 8 wraps and the post is 8 feet high, what we have here is 8 right triangles. Each of these would make a right triangle where the hypotenuse is the ribbon, right? And so I can use a little geometry. Probably the most famous formula in geometry that has to do with right triangles is what? Pythag, that's right. So remember what Pythag is? It's if you have a right triangle that has legs A and B and hypotenuse C, then the relationship a squared plus b squared equals c squared will hold, right? All right. Well, we know a couple things about these right triangles. We know that each one will have one of the legs as 1 foot. And we know that because we know the total height of the post is 8 feet. And we need 8 turns of ribbon. So we need 1 foot between each turn, right? So that makes this leg 1 foot. We also know the other leg because we know the circumference is 6 feet. So when we lay it flat, that base should be 6 feet wide. And so with that information, I'll label the hypotenuse C. We should be able to solve for C. 1 squared plus 6 squared will equal C squared, right? Which tells us that C squared is what, 37? And C is the square root of 37. All right. So this is another one. Use the correct tools. First, we only found how long each turn is going to be, right? How many total turns are we going to have? How many wraps do we need for this post? Good, 8, right? So we're going to multiply that answer by 8, but also we're trying to buy ribbon here. We're not going to go to the ribbon shop and say I need 8 times the square root of 37 feet of ribbon. We probably want to get a decimal approximation there. So I'm going to go into my calculator. I'm going to do 8 times the square root of 37. We're going to go to 2 decimal places. So I'll say he needs 8 rad 37, which is, I should say, approximately equal to 48.66 feet of ribbon. All right. Any questions about that one? Give me a green check if you're good with that. We've only got a couple more. I think the next one is one that I really like. It's kind of a riddle type one. All right, let's do it. Oh, this isn't, the next one is the one that I'm a big fan of. Okay, we got 2 more. This one is interesting though. I just want to get your take from an intuitions perspective. So be ready to give me your answer in the chat. Jill and Jack ran a 100-meter race. Jill won by 5 meters. That is, Jack had run only 95 meters when Jill crossed the finish line. They decide to race again, but this time Jill starts 5 meters behind the starting line. Assuming both runners run at the same pace as before, who wins? Put your vote in the chat. Who wins that, Jack or Jill, the second time? Tie. I got a lot of ties, and I think that's the common intuition, but let's look at this. So Jill can run 100 meters in the time it takes Jack to run 95 meters. Can you agree with that? So this is on the second race. Jack is going to start here. We'll put Jill back here. So she's 5 meters back, right? All right, so that's 5 meters. But they're still racing to the same 100-meter finish line, right? It's just Jill's going to be running a longer race this time. So let's say that's over here. So that's the 100-meter mark from the start. It's just Jill is starting negative 5 meters back. Now, I just said that by the time that Jack runs 95 meters, let's say that that's 95. So he still has 5 to go. So Jack has run 95 meters. How far is Jill able to run in that same amount of time? We just said this, right? 100 meters, correct? So Jill will have caught up to him by that point because she'll have run that 95 meters, but she would have had also run that additional 5 meters. She would have run 100 meters, right? And they still have 5 meters to go, but who's running faster? So who's going to win? Jill still wins. So yeah, I think the intuition is that it would be a tie, but if you draw it out or diagram it, we can clearly see that Jill is going to catch up to Jack at the 95-meter point. There's still 5 meters to go. Jill is running faster, so she's going to win. All right, let's do the last one. So that one's kind of counterintuitive, a little bit fun. Here's the last one. So I'll give you the general idea. We don't have to read verbatim through the problem, but here's the deal. You have a cup of coffee and a cup of milk. They're the same size. What you do is you take a spoon of milk, you stir it into the coffee. Then you take a spoon of that mixture. Okay, so you take a spoon of this mixture and you're going to stir it into the milk. Is there more milk in the coffee or more coffee in the milk at the end of this? Put your vote in the chat. Is there more milk in the coffee or coffee in the milk? Megan's the first to step up to the plate. She says more milk in the coffee. All right. Megan's getting some people on her bandwagon here. Any more votes? Any reasoning? Anybody want to give me reasoning why you think there's more milk in the coffee? That seems to be there's more milk in the milk cup than coffee in the coffee cup. I want to know the other way around, Colin. It's the same question, but is there more milk in the coffee cup or more coffee in the milk cup? Anybody have reasoning why they think more milk in the coffee?
When you put the milk into the coffee the first time, you're putting just milk.
Pure milk.
Yeah, but when you put coffee, the like mixture, then it's not just coffee.
That's a good explanation. It's diluted, right? I like that line of thinking. But let's see. So here's how you can do this one. What we're going to do is simplify this down. And we'll say that we're looking at milk and coffee molecules. Let's pretend there's 10 of them. There's more than that, but it shouldn't matter. So I'm going to use blue for milk like it's Star Wars because white won't read here, but I'm going to do 10 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my coffee. There's my milk. Okay, so first we're going to put milk in the coffee, right? So let's say a teaspoon represents 2 of our molecules. I'm going to randomly select 2 molecules. Boom, they get intermixed into the coffee. So here's kind of stage 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then I have these 2 milk molecules in my coffee, right? And over here I have two fewer milk molecules. All right, so now what I'm going to do, I'm going to stir it up, and I'm randomly going to choose 2 molecules from my milk coffee diluted situation, and I'm going to stir them back over here, right? Okay. Well, stirring, all that basically does is it randomizes the molecules that we're going to choose here. So give me one situation. So I'm going to randomly choose 2 of these molecules on this side, and then I'm going to stir them into the other side. Give me one situation that I could choose. I could choose 2 coffees, right? So I could stir it up. I'll go in with my spoon and I could scoop out 2 coffees, right? In which case, those 2 come over here, and now I have this situation, right? So if that were the case, here's what it would look like after I stirred both of them up. In that scenario, is there more milk in the coffee, more coffee in the milk, or are they even? Yeah, they're even, right? Here I have 2 milk molecules in my coffee. Here I have 2 coffee molecules in my milk, right? They're even. All right, let's go back. Let's do another one. L said another situation. So let's go back to just having our milk molecules. We have our coffee, and we haven't selected them. So there we did 2 coffee. L says, well, we could randomly have selected 1 coffee, 1 milk, right? That's another situation that could have happened. In that case, I'll take one of these and one of these, and they both go over there. So it looks like 1 milk, 1 coffee, and then I'll remove that coffee. I'll remove that just for the visual. Boom. Now, what about now? More milk in the coffee, coffee in the milk, or even? Yep, still even. Okay, what's the last possible scenario that could have happened? We did 2 coffees. We did 1 coffee, 1 milk. What's the only other possible combination that we could have gotten there? 2 milks, in which case I just take these 2, I go back to here, and they're still even, right? So actually the answer, it is counterintuitive, is that if you carried out that scenario, you should have the same amount of coffee in the milk as you have milk in the coffee.